Okay, let's continue and let's see an example about the k-nearest neighbor. Well, we are using a anonymized data. So this data has already been anonymized and transformed. And as you can see, you see the columns and you see all the values, but you don't really know what they are. And sometimes well, you may have to deal with this kind of data, especially it is some confidential data. Your business partner wants you to work on this kind of data, but they don't want to just review the original data set for you. So what you may end up with having is a anonymized data, and also it is a transformed data. And one of the way people may use to anonymize and transform the data is the PCA. If you see some data set like this, well, you may find this is not particularly interesting, but well, anyhow, you can still run any machine learning algorithms on that. So for this data set, we have 10 columns and one target class. The target class has only two possible values, 1 or 0. What we are going to do is we are going to start from dropping the target class, and we only have the matrix of all features, and we call that matrix features. And after that, we want to do a train and test split. We are splitting all the features into the training set and the testing set. And for this column, target class, we are also splitting that into the training labels and the testing labels. So they're X train, Y train, X test, Y test. After that, we want to build a k-nearest neighbor. To make the case really simple, let's only consider the k value to be 1. So we are doing the 1 nearest neighbor. And we want to fit the model with the X train and Y train. Then we want to do a prediction. And this is the predicted values. And you can see there are a bunch of zeros and ones. Well, this is not quite easy to read. If we want to evaluate the performance of the k-nearest neighbor, the easiest thing we want to do is we want to put the results into a confusion matrix. Remember, we only have zeros and ones in this case, so it will give us a 2 by 2 matrix. And if you see a confusion matrix, remember the way to read that is each column is a predicted label. So for example, if you see the 144 and the 8, they are the predicted labels to be 0. And for each of the row, that is a actual label. This means for 144 of them, they are labeled to be 0 in the real dataset. And then our model also predicted that to be 144. So, well, that is a pretty big number. And similarly for 130, there are 130 samples labeled as 1, and then our model also predicted them to be a 1. So, well, that is pretty impressive. And if we want to do a classification report, and you can see the precision and the recall of the zeros and the ones, and we also have the F1 score. The next thing, well, since we only have a 0 and 1 as the possible labels, actually in this case, we are predicting the values to the sample to be positive or negative. And if this sample is positive, and we also predict that to be positive, and then we say it is a true positive. Or if we predict that to be a positive, but actually it is a negative, and then we call that a false positive. So the next, well, what I want to say is when we are evaluating this result, we are considering a false positive and a false negative to be wrong, and they are punished in with the same weights. So a false positive, that is a wrong classification, and a false negative, it is also a wrong classification, and we are considering them to be equally bad. Well, in reality, it may not always be that case, and for some cases or for some scenarios, for a false positive, you are going to be punished much harder than a false negative, or vice versa. So let me give you an example. Say if I'm selling cars, I'm a car salesman, and if when I see a customer and I have the customer information, then I want to make a prediction. The prediction is whether this customer will be interested in luxury cars or not. So if my model predicts that this customer might be interested in luxury cars, and then what I'm going to do is I'm going to try to convince my customer, okay, we have luxury cars on sale and they are pre-owned luxury cars. They're cool, they're in good shape, but they're not super expensive. How about do you want to consider that? So if my model classify the customer to be a positive, this person might be interested in luxury car, but actually this person is not. What is that? I classify this person as a positive, but actually this person is a negative. So this is a false positive. We predict this person might be interested in buying a luxury car, but actually this person is not interested in that. So a false positive case. And if from a car salesman's perspective, what did I lose? Well, I just wasted a couple of minutes, right? And consider another case. If someone is indeed a potential buyer of a luxury car, however, I didn't remember my customer there is an option. And then what is my loss? Probably thousands of dollars, right? In this case, a false positive, I lost something. Probably my customer is a little bit annoyed, or I wasted a couple of minutes. It's not a big deal. However, if I have false negative and I should sell a car to this customer, but I didn't, and this will be a big money loss. Well, the point I'm trying to make is, even though, we are treating false negative and false positive as equally bad cases, they're not always that case. Sometimes you do have to tailor the evaluation matrix of your machine learning model before you run the machine learning models and make the evaluations. Sometimes, the evaluation matrix can be tricky too. So the next part, here is a challenge for you guys. Try to do a Minkowski with the PS3. So degree 3 Minkowski, and then let's see what you get. And after that, try to do a Minkowski with the PS1. Okay, Minkowski with the degree as 1, that is Manhattan, right? So try Minkowski with the PS1. That is one machine learning, one model. And then try to use Manhattan as another model. And for both of them, you want to try the n neighbors to be 7. So do you have the same result? Two machine learning models, one with Manhattan distance, another one with Minkowski but the degree as 1. Theoretically, you should have the same thing. And do you have the same thing? Try to write the code by yourself and then try to figure that out. So I will see you in the next video.